All right. So this topic is is significant figures, and what a significant figure is a way to measure the reliability of measured data. All right. Sig figs are a good thing. The more sig figs there are, then the more confidence we have in that number being correct. Now, there are a bunch of rules, but first we need to understand the context. How does this even come up and why does this even exist? So, for example, let's say that I have a Matchbox car, right? And let's just say for some reason I need to measure this. So, let's say that I have a crude tool. Let's say I have an unmarked ruler. Okay? So there's a ruler, it's unmarked. I have to guess by looking at this, what's the length of this toy car? All right, so here, what do we know? We know that a ruler is 12 inches, right? So, or I'm sorry, here, let's keep this metric, right? So we know that a ruler is 30 centimeters. Okay, so is this, it's obviously less than 1 foot. Is it less than half? Is it less than a quarter? It's kind of hard to say, right? So if we bisect this, and this is half, yeah, arguably it looks like it's just shy of a quarter, right? So we would call this 0.2. I should use a different color here. 0.25. But here's the problem. Since I have no lines, I cannot estimate that 5. So we have to call this either 0.2 or 0.3. So let's just call this 0.3. We think it's 0.3. Okay? Now, let's say that Apple releases a new ruler. And this ruler is marked in centimeters. All right? So each one of these lines is a centimeter. And then it goes on the entire length here, but we're just gonna work on this side. So 0.1, or I'm sorry, not 0.1. This is just 1, 2, 3, 4, 5, 6, all right, and so on. Do you guys remember when I told you how to measure? You estimate in between the smallest markings. So we need to figure out what we know for sure, and then we can do some estimating. So is this past 0.1? Yeah, definitely. It's past 0.2, it's past 0.3, it's past 0.4. I'm sorry, it's past 4 centimeters. Look, it doesn't make it to 5 though, right? So we have to come up with a measurement. Somewhere between 4 and 5 centimeters. It's the 10th place that we are estimating. What would be a fair estimate for the 10th place? Sure. Okay. Let's say Apple releases, ruler 2S. And not only is it marked off in centimeters, it's marked off in tenths of centimeters. That was not the scale, but we're going to pretend it was. Actually, here, let's do this. Oh, yeah, that didn't work. All right, let me redraw this. All right, close enough. Okay. So now All right. Take some precision here. This is definitely past 4 centimeters. It's 4.1, 4.2, 4.3, 4.4, 4.5. And look, it's just a hair past 4.6. Somewhere between 4.6 and 4.7. And we are allowed to estimate because this tool is marked off in tenths. So we are allowed to estimate the hundredth. So what should we call it if it's right next to 4.6? Sure. 4.61 centimeters. So it took 3 different measuring tools, but we nailed down to the hundredths place what we think the length of this toy car was. So are you guys okay with the concept of improving the tool, getting more lines, and then your measurement ends up having more numbers? Okay, so we're going to come back to this example, right? So let's talk about sig figs then. A significant figure in a measurement, when you look at a number, there's a couple of rules. The first rule is that all non-zero integers are significant figures. All numbers that are non-zeros. So a number like 4.61 has 3 numbers. They are all non-zeros. Those are all significant. Okay, so that has 3 sig figs. A number like 100 or 12,151. There's 5 digits. They are all non-zeros. There's 5 significant figures. Uh-oh, my 5 looks like my S, as I've learned. Okay, there we go. Are you guys okay with that? All right. Zeros is where this can get complicated. So we need to talk about the different types of zeros. You might not have paid much attention to zeros before, right? But where they are located means something. The first type of zero is what we call a leading zero. A leading zero precedes all non-zero integers. All right, so when you look at this number right here, 0.0025, those zeros come before any non-zeros. Anything that comes before a non-zero is what we call a leading zero, and those are not significant. They do not count. Now, the 2 and the 5 are non-zeros, so those count. So therefore, this number has 2 significant figures. Okay, it doesn't matter how many zeros there are. You could have a huge line of zeros. The point is, they're all leading zeros, and therefore they do not count. Okay? To give you an idea, leading zeros are like they tell you what scale that you're working on, but they're not actually something that's measured. Okay? Meaning what scale, meaning like how big or how small of a scale you're working on. All right, so those are leading zeros. Captive zeros are in between non-zeros. They do count. So the number 1.00003, I say that right, there's 4 zeros there. Those 4 zeros are trapped between the 1 and the 3. So they're captive, they do count, therefore this number has 3 sig figs. 6 sig figs, sorry. Okay. How about a number like this? That has 3 because the first 2 zeros don't count. Right? The non-zeros count, the trapped zero counts, therefore there's only 3 significant figures that count. Okay. The third type of zero is what we call a trailing zero. And this is the most confusing part. You got 2 types of trailing zeros, right? You've got a trailing zero where there is no decimal point, like here. See this number right here, 100? The rule says that non-zeros count, so this counts. Trailing zeros do not count if there isn't a decimal point. That's why 100 has only one sig fig. But look at the second example. This, you would also read this as 100, but the difference is it has a decimal point and it has 2 additional zeros after the decimal point. So you've got 1, 2, 3, 4 trailing zeros, and you have a decimal point. A decimal point is like a stamp of authenticity. Okay? If it's there, all trailing zeros count. So this number has 5 sig figs. This number, 100 with a decimal point without zeros, would have 3 significant figures because we have 2 trailing zeros now with a decimal point present. Now I need to mention that when you write scientific notation, the 10 squared here, this is not part of the measurement. All right, the 10 in scientific notation, that's also giving you a sense of scale, how big or how small something is, but it's not part of the measurement, so therefore you ignore it when you're counting sig figs. Okay, so I'm going to put some numbers up here, and I want you to kind of just look at them, and let's talk through how many sig figs these examples have. Okay? Take a second, jot those down. All right. Can I get someone for the first one? Yeah, Sheila. Yes, there are 2. These 2 are significant. The zeros are not because those are trailing zeros and there's no decimal. Okay. What about the second one? Michelle?
3.
There are 3. We have 2 non-zeros. We have a trapped 0. We have a trailing 0, but there is no decimal, so the trailing 0 does not count. Okay, what about the third one? Kayla?
2.
Just 2. The leading 0 does not count. Leading zeros never count. Okay, what about the fourth one? Yeah, Dominic. 2 as well, yep. 3 leading zeros, 2 non-zeros. There's only 2 sig figs in that number. All right, let's move over to the next example. 0.00102. Yeah, what do we think? Elijah?
3.
There are 3. 2 non-zeros, a trapped 0, and then 3 leading zeros, so only those underlined ones count. Okay, and the last one, Matthew. I'm sorry, Armand. Richard.
4.
Yeah, why?
There are 2 leading zeros. There's 1 trap 0, and then there's a trailing 0 that's got a decimal. So it counts as a sig fig.
Okay. How are we feeling? Okay. All right. There are numbers that are intended to be exact, intended to be whole. All right, so things that are counted, any counted objects like apples, people, cars, things that are not meant to be divided are what we call counted objects. And counted objects have an infinite number of sig figs, all right, or think of them as exempt from the sig fig rule. Okay, you don't bother counting sig figs. If I say that there's 29 people in here, right, that number 29 does not have 2 sig figs, even though it looks like it has 2 sig figs. Things that have significant figures are things that are measured. Inches, grams, milliliters, seconds, watts, pounds, things like that. Okay, counted objects are not subject to sig figs. Also, there's what we call exact conversion factors. Exact conversion factors are things like there's 100 centimeters equal to 1 meter. That relationship is not counted out, that is defined. By definition, by metric definition, that is a truth. And so when I look at that number 100 centimeters, I don't say there's 1 sig fig. I realize this is an exact conversion, and so that has infinite sig figs, and that has infinite sig figs. Okay? So, now that we know what sig figs are, I said I would go back to this. Going back to our Matchbox car here. In our first attempt at measuring, how many sig figs did we have? 1. In our second attempt, how many sig figs did we have? 2. In our third attempt, how many did we have? 3. So do you see how changing the precision of the measuring device changes the number of sig figs? Yeah. Okay. The more numbers that you know for certain, then the more accurate your number is. All right, the more reliable that number is. Okay. Have you ever seen a caliper? A caliper is an engineering tool that's used to measure. So, let's say if you were an engineer, you would use a tool that looks like this. Let me find some space here. It looks like this. So here's your car, and it literally looks like a mouth, right? And there's like this little wheel with grooves, and it pushes or pulls the jaw, and wherever that jaw lines up, it gives you an exact reading, right? Now, who has one of those? You don't give one of those to kids, right? Because they're expensive. They have to be calibrated, right? They have to be sturdy. So, but if we wanted a very, very, very accurate measurement of the length, we would use something like that. Okay. All right. There are rules for using significant figures. See, significant figures don't exist in a vacuum. There's actually a reason why we have to understand what sig figs are. Is because the effect of measuring not enough sig figs is like a domino effect. If you're not accurate at the beginning, there is no way the end product can be accurate. Okay? So, there's 2 rules. The first rule is for multiplying or dividing. Whenever you multiply or divide a number, the answer, the product, can only have as many sig figs as the fewest number of sig figs. So, if we multiply 9.325 by 1.2, your calculator will tell you the answer is 11.19. However, you took a number where you were so sure that you had 4 sig figs, and you multiplied it by a number that you were only sure of 2 sig figs. So there's no way that your answer can be more certain than the least certain number. So you're limited. So we have to round this. We have to say 11. 11 is the answer because 2 sig figs is all that I am allowed. Okay? Let's try the next one. So 25 times 1200. So the calculator says 30,000. How many? I have 2 sig figs in 25. How many sig figs in 1200?
4.
I see 2 non-zeros. I see 2 trailing zeros, but I do not see a decimal. That's 2. So both numbers have 2 sig figs. My answer can only have 2 sig figs. If the number 30,000, the way I wrote it, how many sig figs does it look like it has? It looks like it has 1. But I'm supposed to have 2. What did I show you how to do earlier? Yeah, scientific notation. Hello.
Are you using these?
I am not. You may use them.
Hey guys.
Hello.
This is Mr. Tro. Say hi.
I'm the good looking one on that syllabus. That's me. You know what I'm talking about.
If you look at it upside down.
Any way you turn me, I look good.
That's right.
Go away. All right. So I need to write this so that it has two sig figs. 3.0 times 10 to the fourth. That is the number with two sig figs. So scientific notation will help you accurately portray a number with the correct sig figs. Right? You just have to remember to use it. Okay? Let's try the next one. This time we're dividing. So 15 divided by 0.1156.
On the calculator comes out to 1, 2,
Yeah, calculator likes to tell me lots of numbers, right? But we know that we cannot possibly express that many sig figs because 15 only had two sig figs. So I can only have two. We're gonna have to call it 130. By the way, this little guy, you ever seen this character? It's called the tilde, with squiggly line. We use that when we indicate that a number has been rounded according to the sig fig rules. Okay? Now, that's not a universal thing. I'm just doing that here because when I look at your work, it lets me know what you intend your final answer to be. Okay, so just get in the habit of doing that. Okay, so multiplication or division, it doesn't matter. The rule is the same. Fewest sig figs determines answer sig figs. Got it? Okay. All right. Adding and subtracting. So adding and subtracting is a different process than multiplying and dividing, right? And so let's take this example here. I have three numbers that I need to add up. So I line them all up over the decimal, okay? So I add them all up, and so this is my raw answer, 16.375. But here's the thing. When we look at this number right here, in this measurement, what is the uncertain number? It's the 5. The 5 is the uncertain digit. Imagine we used a tool to measure this, and we were sure about the 12, we were sure about the 10th place, but we had to estimate the 100th place, right? The estimated digit, the last digit, is the one that is uncertain. Okay, so the first number, the 5, is uncertain. The second number, 1.1. That number was measured by a tool that only had increments, whole increments, right? Like 1 centimeter, 2 centimeter, 3 centimeter. There were no lines in between. So that 0.1 is the guess. That 0.1 is uncertain. The last number, 3.125. Well, the last digit, yeah, the last digit is uncertain. So, if I told you I'm going to add three numbers together, one of them is only sure in the 10th place. That's this one. One of them is only sure to the 1's place, and one of them is only sure to the 100th place. When you add them all together, your answer can only be as sure as the place that they all have in common.
Which is the 10th place.
Right. They all have a 10th place. Do you see that? They don't all have a 100th place, and they don't all have a 1,000th place. So I usually draw a line, a dotted line like this, and shows you what you're going to have to drop. We're going to have to drop the 7, and of course, when you drop the 7, you're going to round that 3 to a 4. Another way of stating it might be easier for people to conceptualize. The answer can only have as many decimal places as the number with the fewest. So the fewest number of decimal places of all of these numbers was 1.1, and so therefore our answer will only have an answer up to the 10th place. So the rule for addition and the same rule for subtraction. It's the same rule. It's based on how many decimal places there are. Okay, so in a problem, identify, are you multiplying and dividing? Are you adding or subtracting? Because that changes how you go about determining what the answer is. So let's do a couple of examples. Actually, let's take a minute. You do a couple of examples, and then we'll evaluate. Try these two. Okay. I apologize for the first example not being aligned. I guess I had to tab that one over. So it's easiest if you make the effort to make sure the numbers are aligned. It's easier to see. Okay, so this is your raw answer, right? But of course, what do they have in common? They only have the hundredths place in common, so your answer will be rounded to 3.42. Did you get that? Yep. All right, good. The next one, 1.000 minus 0.0004. Okay, so you're gonna have to do some borrowing here, right? So we're gonna get 0.9996. Yeah. Right, we're only allowed a 10,000ths place, okay? The 3 decimal places. So when you drop that 6 by rounding rule, this goes back up to 1.000. So it does not appear to have changed. Right, it's like borrowing a nickel from a millionaire, right? It makes no difference.
You would accept 1.00 or what as your answer?
I would accept the number that has the correct number of sig figs. So it would have to be 1.000.
Oh, yeah, that's good.
Okay. How are we doing?
Pretty good.
2 rules: multiplication, division, subtraction, addition. So can this get complicated? You can. Yes, it can.
Doesn't feel like chemistry. It feels like
Well, you need this is math in order to do chemistry, right? Okay, so there is this issue of changing operation types. So let me explain what we mean by this. If you have mixed operations, like meaning you have both a multiplication and an addition in the same problem, first of all, it's math. So you always follow order of operations, right? But because you have 2 different rules, because you're carrying out 2 different operations, you must carry out the first operation per order of operations, and then when you are changing the operation to something else, that is when you must round. You must round the number before you set it through the second operation. So when we look at this example A, what is the first operation we're going to be doing, the multiplication or the addition? Multiplication. So we will multiply those 2 numbers together. Okay, so 2.5 times 15.1. Just use my calculator for this, be lazy.
37.7.
Okay. 37.75. That is the product. So to that number, I will add 0.75. But I am now changing from a multiplication operation to a different operation, which is addition. So because of that, I must round according to the rules of multiplication before I use it in the second operation. So this must become 37.8. Do you guys see that? 3 sig figs in both of those numbers. So I can only, the product can only have 3 sig figs. Now, 37.8 plus 0.75. And then, since I am done, and my last operation was addition, I must round according to the rules of addition. So that means this answer will be what?
38.6.
Yes, right, because we're going to have to cut this off. Right, 38.6. So this is called mixed operations, when you're doing both types. If you are carrying out both types, you have to follow the rules of rounding before you carry out the next type of operation. Yes, question?
Why it can't be 38.5?
Philosophically, or what do you mean?
Look at the math, that's 38.5. Do we run it? Or do we?
It's 38 point. Well, you're dropping the 5, right? Aren't we dropping the 100th place, the 5 in the 100th place?
We just,
So by rule, anytime 5 and up rounds up, right?
Oh,
So if it's the 5 we're dropping, then we have to round the 5 up to 6. Okay. Okay, let's try the second example. Look, we have parentheses. Where do parentheses fall in the order of operations?
the first thing.
The first thing. So we have to do what's in the parentheses first. So let's do that. Okay, so subtraction yields 15.16, but as we just discussed, this will have to be rounded to 15.2, and then we take that, and now we divide it by 0.55, 0.55 to 0. Okay, so we are allowed 2 sig figs. The 27.63 repeating will just round up to 28. Okay. Here's scientific notation, which we had previously talked about. Anytime you need to turn a number into scientific notation, express it as a number between 1 and 10, and then determine the power of 10 necessary as a multiplier. Right, so 1,348 is 1.348, but you have to move the decimal 3 times, so the 3 goes back. All right, that's, and since for good measure, this is the end here. Let's just do these last 3 here. Write these in scientific notation. Take a minute. All right, hopefully you got those. How come I have those extra zeros on part C?
Because they're trailing zero. There's a decimal.
Yes, there's a decimal and they're trailing zeros. That means they do count. That means they actually are intentional. All right.